Welcome everybody to our new session of seminars here at Thursdays at BrIAS. So today we have we will have 3 seminars, all the 3 seminars touching subjects around the world of control and from 3 speakers from 3 different Belgian universities. So I'm going to introduce the first one, that is Gianluca Bianchin from UCL, that, let me also tell this, had the idea of visiting us last week that he was here for another seminar, and so we decided to directly tackle him and say, okay, then you give a seminar next week. So you know that when you pass by, this is one of the risks that you are going through. So I leave the stage to Gianluca, and I'm very curious to see what he will present to us.
Okay. Thank you very much, Emanuele. Well, I think I will continue to come at the next seminars. So if you give me the opportunity, I can give more talks. I can present other things, other projects that I have ongoing. Well, so thanks a lot for the introduction. My name is Gianluca Bianchin. I am an assistant professor of applied mathematics with the ICTM Institute at UC Louvain, which is not far from here. And today I would like to talk about some of our recent work on transportation systems and in particular on internal models for optimization. So transforming transportation systems is one of our major priorities these days because if we look on the news, we quickly realize that carbon dioxide levels are now higher than ever in human history. And so making transportation systems more efficient, more sustainable should be one of our top priorities for the next few years. If you look at the repartition of carbon emissions in the European Union by sector, we see that in 2025, transportation is the sector with the highest emission. So even a small change in transportation can have a huge impact for our environment and for our health. In Belgium alone, the economic cost of externalities associated to transportation and congestion is 5 billion euros, which is 1% of the total GDP of the country. And when I talk about externalities, what I'm talking about is a set of costs that are passed down to us, to the general public, associated with congestion. These includes costs related to higher pollution, costs associated to accidents, noise, health problems, and so on. So it's a huge cost just for the country of Belgium, and you can imagine this escalates for the whole European Union. So the way I like to look at transportation systems is by considering them a network of networks. So what this means is that transportation systems in reality is just an interplayer between the various elements that compose it. On the one hand, there are the end users, which are us. Whenever we use transportation, whenever we buy a product online, we are making it delivered to our place. We are using the transportation system. And on the other hand, the other players of the framework are the various fleet owners, vehicle owners, railway companies, micromobility companies. As you can see here, there is a very large number of players that all interact by means of this complex system in the middle. So today I would like to introduce my talk by discussing some of the emerging features in transportation. Well, the first one has to do with making them more sustainable and facilitate transition. So one of the things that we have been trying to do in the past few years is to electrify the transportation system. This adds new complexities because we are coupling it with the power distribution system. We are changing the type of vehicles that we are using. Now they are smaller and smaller, and so this changes a little bit the way we plan it, the way we design parking and lanes and so on. Now we are increasingly working with shared mobility. We are all familiar here in Brussels with the concept of sharing bicycles, sharing cars, and so on. We are also all familiar with multimodal transportation, where we can use a light rail, a bicycle, a train, all to just do our morning commute. A second emerging feature of modern transportation systems is related with their increasing complexity. So nowadays we can monitor the state of the transportation system, we can visualize where congestion is located in the city, and we can plan accordingly. So if there is a strike, in Belgium is very common, we just plan alternatively, we take the car that day. This feedback, the fact that we can monitor the transportation system is something relatively new. 10 years ago, we were not able to measure what was the current state of transportation today. Other emerging features are, of course, connected vehicles, which add functionalities but make also the system more fragile. It is the use of electrified transportation versus combustion engine and so on. But what I would like to really focus on today is the notion of faster dynamics. So as transportation systems, let's say, advance and revolutionize every day, the main important feature that we should concern from a point of view of control and optimization is related to how fast they are becoming. So when we monitor transportation using our phone, and we change our routing preferences, our commute preferences based on the current state of the system, we are adding a feedback loop in the transportation system. That is because we're monitoring what is happening and we adapt accordingly. This adaptation is what generates a feedback loop. Similarly, when we purchase merchandise online and we request overnight shipping, which now is very common, we are, let's say, we are very demanding towards the transportation and logistics company, which need to make it happen to deliver the package to you the following day. So this demand of, let's say, making it extremely fast, requiring deliveries very quickly, is changing the dynamics, is making the system much faster than it used to be. And then so on. I can continue with examples. When there's a strike in the trains, then we can decide to take a bus or a light rail instead, and this also creates a feedback loop. So with this motivation today, I would like to talk to you about how we can make decision-making in dynamic environments, in transportation systems precisely. My talk is organized into three main parts. I first would like to talk about, let's say, decision-making. In the second part, I would like to talk about decision-making when the transportation system, in this case, has dynamics that are non-trivial. So we need to account for this as if it were a plant to be controlled in control systems. And then finally, if I have time, I will talk about some particular problems in transportation that we can solve with the methods that I will talk about. Okay, so I would like to begin by talking about decision-making in dynamic environments, and most of the content that we talk about is included in one of my recent works with Brian Vanscoy at Miami University in Ohio. So making decisions, especially in transportation, amounts to solving an optimization problem. So a general optimization problem is what I am summarizing here on the left. So we want to make a certain decision X, that's our decision variable, that minimizes a certain loss function. This loss function F describes the performance of the transportation system, for instance, or it describes our loss that we want to minimize. So I'm going to make, let's say, common assumptions on this cost. The focus is not on making optimization more general, so I'm going to assume that the cost is convex, it is smooth, it has the nice properties that we are used to. But the main feature I will focus on is on this variable theta. This variable theta, I am going to look at it as a parameter that parameterizes the optimization. And the particular feature is that this theta is time varying. It changes with time. So because some parameters in the optimization problem change with time, that means that at every time t, I am in continuous time here, so we'll denote time by t, At every t, I will have a different optimization problem to solve. This is illustrated here on the graph on the right. So at time t1, I will need to solve an optimization problem. Then time moves to t2, I will have a different optimization problem to solve, and so on. Okay, t3, t4, so at every t, I have a different optimization problem. I'm going to impose some regularity assumption on how this theta changes. I'm going to assume that it is deterministic. I will not focus on stochastic framework today, but this can be done. And all I'm going to assume is that this theta is differentiable and its derivative satisfies some nonlinear function. Okay, so it's a very general assumption. It just asks that theta is sufficiently smooth and is deterministic. So most of the focus in the first part of the talk will be on making decisions in dynamic environments, which in the setting of optimization, it means to make optimal decisions. So this means that at every t, I want to compute x star of t, which is the optimizer of this optimization problem. So that's the goal for the next few slides. So there are many algorithms in the literature that can be used to solve time-varying optimization, as I described. Most of them are algorithms that are based on gradient-type methods. What this means is that we have access to some oracle evaluation of the gradient. This means that at time t, I have access to the gradient of the cost at time t. And in the literature, you will find a very broad range of methods that can be used, but perhaps the two most important ones, I would like to discuss them now. The first basic method is what I will call basic gradient flow. So in the basic gradient flow, I update my, let's say, my estimate for the optimizer. This x is an estimation for the optimal decision. I update my x in the negative direction of the gradient. This is the typical, the most basic approach we can think from optimization. So down here I show an illustration of what happens if I apply the basic gradient flow to the problem that I described. So with the orange line here you see the temporal evolution of the optimizer. That's what we want to compute, what we want the algorithm to compute. And in green, on the other hand, I am showing the state of the optimization algorithm. So what we can see from this plot is that the algorithm doesn't perform very well. Indeed, it doesn't get any close to the optimizer as time evolves. And indeed, in this case, for this particular method, what can be shown is that it computes only an approximate optimizer. So it doesn't depart away. It stays close to the optimum, but it does not compute the optimum exactly asymptotically. So because this method has some flaws, alternative techniques can be found in the literature, and the most important one goes under the name of the class of prediction correction methods. So the structure of the prediction correction is illustrated here on the right-hand side. So the first thing I would like to observe is that this H is the Hessian of the cost. So I need a cost that is twice differentiable. They need stronger assumptions. And then I can interpret this term in orange. This term looks very much like what I had in the basic gradient flow. That is, let's say, a gradient flow step. But then the prediction correction method has a second adjustment, which is called the prediction step. This anticipates how the problem will change in the future. Okay, so if I look at this depends on how the gradient changes with respect to the parameter times the temporal variability of the parameter. So it makes a prediction of how the problem will evolve. If we simulate this algorithm, this works very well. Here again in orange you have the optimizer, and in green you see the state, the estimation given by the algorithm. And as you can see, the two, let's say, the error between the two converges to zero asymptotically. So these methods work rather well. However, it has some limitations. First of all, it relies on many strong assumptions. I need the cost to be strongly convex in order for the Hessian to be computable. I need to know the temporal variability of the problem that enters explicitly in the optimization. And I also need to know how the problem changes with time. So this makes a lot of very stringent assumptions, which we realize are much stronger than what is needed in reality. So the framework that we would like to take in this line of work is to reinterpret the design of optimization algorithms through the lens of control systems. And I would like to describe this, how we're doing this using this block diagram. So here on the left-hand side, you see the temporal variability generator. This generates the theta with time. I would like to stress that these may be known or may be unknown. I'm not making the assumption that I know it. It is just there. It generates theta. Then, in this white block, what I am computing is the gradient of the function. So this is what I earlier called gradient oracles. So if you give me theta and you give me, let's say, an approximation for the optimizer, this white block computes the gradient of the cost function. So if I want to compute an optimizer, then that corresponds to what we call exact asymptotic tracking. That means that asymptotically, I want the gradient signal to converge to 0. If I do that, that means that asymptotically, I am converging to a critical point, a point where the gradient is 0. Okay, so that's, let's say, the basic framework of methods that rely on gradient oracles. Now I would like to look at this from the point of view of control systems. So a control theorist, what it would do is it would attach control algorithms to this plant. So I'm going to look at this gradient signal as a plant, and I'm going to look at, I'm going to attach to it this gray block, which I can think of it as a controller, but in reality it is an optimization algorithm. Okay? And so what I'm going to need to do is I'm going to, let's say, need to design this gray block so that y of t converges to 0 asymptotically. So that's, let's say, the translation of designing optimization algorithms into designing a controller. So for this gray block, I'm going to, let's say, assume some very general form to put in here. I'm just going to assume that the optimization method will have an internal state that I will call z, an internal state to the method. And the method will generate an estimation for the optimizer x. Okay, so that's the general form of optimization methods I will look at today. The functions f and g here, they are free for the moment. And if I want to design an optimization method to make optimal decisions, well, that can be formalized as follows. I will want to design f and g, these two functions, such that y of t tends to 0. And that's how I related an optimization, designing an optimization algorithms into designing a controller. Before talking about how to design this optimization method, I first need to pose, let's say, a more fundamental question, which is what I call here problem 0. What is the minimal knowledge that I need to design this method? What do I need to know to design this technique, to design this optimization method? So there are at least two types of knowledge that I can look at. One is knowledge with respect to the temporal variability, so with respect to the temporal variation. Here there are, let's say, many assumptions that I can make. I can say that, well, theta of t is measurable, or it is known. This assumption commonly made in the literature. Another assumption that I can make is that I know the temporal variability. So S of theta, the vector field that generates the temporal variability, can assume it to be known. Or I can further reinforce this assumption and assume that both of them are known, which is what here I called E3. Okay, so I'm not asking you to memorize all of these assumptions. This is just to say that in the literature there is a broad range of assumptions that can be made. And it is, let's say, there are many technicalities to be discussed here. The second type of assumptions that one can make are with reference to the optimization. Okay, so what do I know about the cost that they want to minimize? Here again, I can make different types of assumptions. The first one, O1, here I only assume that I have oracle evaluations. So I give you time and you give me back the gradient of the cost. That's the, let's say, least restrictive assumption I can make. Then I can reinforce it into O2. So I can assume that in addition to oracle evaluations, I also have access to the analytical form of the gradient. Okay, so this means this reinforcing it because I'm asking to know the analytical form of a function. And then I can add constraints. I can ask that I want to know the sensitivity of the cost, the Hessian as it is done in prediction correction. I can add higher order derivatives. I can assume that the cost is quadratic and so on. So all these are assumptions that are commonly made in the literature, but what we will want to focus on is what is the least restrictive assumption that I need to make. Okay, so that's what I call problem 0. So to address these questions, I'm going to, let's say, look at it from two different perspectives. The first perspective is the one where I can measure how the problem changes with time. So going back to, let's say, my control block interconnection, I'm going first to start from a scenario where my optimization algorithm, here the gray box to be designed, also has access to measurements of theta. Okay, this is very common in, let's say, in regret minimization problems, where after I make a decision, I can observe the value of the cost at the current time. So that's typically what is assumed in those type of frameworks. So that corresponds to a scenario where the optimization method has access to the value of the parameters. So when this is the case, what can be shown is that here inside the gray block, I don't even need to consider a dynamic state. I can simply apply an algebraic map. Okay, so I can say that x is some function of theta. Okay, so in control systems, this corresponds to, let's say, an algebraic controller. So to give a result on what can be said about this type of methods, I just want to open a parenthesis on some control technicalities. So I will say that the algorithm exactly asymptotically tracks an optimizer if there exists an initial condition, if there exists a set of initial conditions, such that when I start there, I ensure that the gradient converges to 0. What I want to emphasize is that this is a local notion, the reason being that the exosystem, the model for theta is nonlinear. So with no additional assumptions, the only thing I can hope for is some local guarantees. The second notion that I need to give you, to present to you some results is the notion of limit points of a dynamical system. So a certain point, theta omega, is a limit point of a dynamical system if there exists some subsequence such that when I evaluate the trajectory of that subsequence, I converge to theta omega. And then finally, I have the notion of limit set. The limit set is the set of all limit points of a dynamical system. Of course, these are quite technical definitions. I would like to try to give you an insight of what they mean. Here I have an illustration of typical limit sets for systems. The simplest limit set of a dynamical system is an equilibrium point. This is the case where the temporal variability converges to an equilibrium point. I can also have limit cycles. It's another type of limit sets for dynamical systems, or I can have anything else which goes under the name of chaotic trajectories. That is also the limit set of dynamical systems. Okay, so with this notion in place now, I can give you the first characterization for these, let's say, rather simple type of optimization methods. So what can be shown is that the static optimization algorithm that I just gave you achieves exact asymptotic tracking if and only if there exists, if and only if the algorithm, so that HC mapping, zeros the gradient on all limit points of the temporal variability. Okay, so this just means that when theta converges to its limit points, I need the algorithm to ensure that the gradient is 0. Okay, so while these results seem, let's say, straightforward, the proving this mathematically is not as simple. And what I would like to emphasize is that I'm going to use this basic result to then give more general results for a more complex problem. So this is just an intermediate step. So this brings me to discussing the case where the temporal variability is not known. Okay, which is the slightly more general case. Okay, so I'm going to go back to the previous block diagram, where now you see the optimization algorithm does not have access to theta. Theta is not accessible by the method. And in this case, I'm also going back to the dynamic optimization algorithm that I discussed earlier. So in this case, if we look at this, let's say, block interconnection, we have that the temporal variability of the optimization problem is measurable by the optimization algorithm only indirectly through y, okay, through gradient measurements. So what can be shown in this case is that I can achieve exact asymptotic tracking only when there exists an exponential observer for theta. This is not, let's say, a limiting assumption. It can be shown that this condition is necessary. If I am not able to estimate theta, that means that theta does not affect the gradient. Okay, and that means that the optimization problem is independent of the temporal variability and it can be removed. Okay, so I'm going to make this technical assumption, which requires that there exists an exponential observer. So there exists a system with state theta hat that estimates the state of the temporal variability theta. Okay, so with this assumption, I'm now ready to give you an existence result. So this result says that this dynamic algorithm achieves exact asymptotic tracking. Such an algorithm exists only when there exists some function hc, again, that zeros the gradient. So this function looks very much like, this condition looks very much like the previous one that I gave for the static case. And indeed, it is exactly the same. So the main message here is that designing dynamic optimization methods and designing static optimization methods is somewhat similar. They exist under the same conditions. The next thing I want to talk about is on how we can design them. So provided that they exist, how can I construct an optimization method? So this is what I am summarizing in this slide. So what can be shown is that this dynamic optimization method that I just described achieves exact asymptotic tracking if and only if there exists some mapping that I'm going to call sigma, such that these two conditions are satisfied. So these are quite technical, but I would like to try to break them down. So if I look at the second condition here, this condition says that GC, so this mapping, zeros the gradient on the limit points. So again, we find for the third time the same condition. But what I would like to focus on is the top condition, this one. So this condition, on the right-hand side, we have the vector field of the optimization method. Okay, so that's some property of the optimization algorithm. While on the left-hand side, I have some property of the temporal variability of theta. So I am going to interpret, let's say, this condition as an internal model principle. This condition tells me that in order to exactly track the optimizers, I need the optimization method to be algebraically equivalent to the temporal variability. Okay? Or in other words, the optimization methods need to incorporate an internal model of the temporal variability. And we gave this naming in line with some works done in the 1970s by some very famous authors in control systems, Bruce Francis, Wonham, Davison, Isidori. They worked on linear control and formulated an internal model principle of control theory. So this can be interpreted as the analogous one in time-varying optimization. Perhaps the most important implication I would like to discuss of this result is what is summarized down here. So down here, what we found is that on the limit set of the temporal variability generator, the state of the optimization method, Z, and the state of the temporal variability theta must be related by a change of variables. So there must exist a change of variables that allow me to go back and forth between the state of the optimization and that of the temporal variability. Okay, so just with this characterization, now we can also come out with techniques to design optimization methods. So one particular case is the case where I choose this sigma to be the identity mapping. So that means that Z and theta are identical. So this sigma is just the identity map. And in that case, what the optimization algorithm is just a reduplicated copy of the temporal variability. Okay, so that's what we summarize here. The optimization algorithm must be a copy of the temporal variability. And the method to design an optimization algorithm is summarized here on the right-hand side. I just want to give an idea what this does. So first, I need to find a mapping that zeros the gradient. Again, this comes out again. I need to find some function that zeros the gradient on the limit points. And then the vector field of the optimization algorithm is an exponential observer. So it is a state estimator for the temporal variability. And here you can see how optimization and control are closely interlined in this design method. Okay, so the algorithm is quite technical, so I thought I'd try to give an insight through an example. So if, for instance, we would like to solve a quadratic optimization problem, okay, so here I have a quadratic cost plus a temporal variability that depends on theta. And if I assume that the temporal variability follows a linear model, then the equations that I just gave you simplify a lot. So a mapping that zeros the gradient can be computed explicitly. This is a mapping that depends on the matrices that define the optimization, R and Q. So it can be computed in closed form. The conditions for the internal model that earlier I told you they look a little bit ugly. In this case, they simplify a lot. They become two linear matrix equations, which are much simpler to solve. And then the dynamics of the optimization algorithms are summarized here. So this FC is an exponential observer for the temporal variability. And this GC is just a mapping that zeros the gradient. So I hope I gave you an insight of how the design of methods can be done. Now I just want to connect these to the literature and reinterpret some, let's say, results that we have been using for quite a while. So if I go back to the basic gradient flow method, this was the method that was not capable of computing the optimizers. It was only capable of reaching an approximate point. What can be shown is that this method satisfies the internal model conditions that I gave you, where the temporal variability is a constant, so its vector field is 0. So we can now reinterpret this inexact convergence. The basic gradient flow contains an internal model of a constant, so it can only track time-varying problems that are constant. Okay? And so let's say this was a very interesting finding because we realized that gradient descent methods contain internal models of constant signals. On the other hand, we can also look again at prediction correction methods. I told you that these work very well, but they rely on very strong assumptions. So what can be shown is that these prediction correction methods, asymptotically, they are just a numerical technique to asymptotically compute a mapping that zeros the gradient. So all of these methods, well established in the literature, are just a particular case of all the analysis we have here. There is one more question that is important asking, which is concerned with what do we do if we do not know internal models. So what the message of my presentation is, the only way to track an optimizer is that you need to have an internal model. If we don't have an internal model, what do we do? Well, these results can be interpreted as a fundamental limitation. If you don't have an internal model, you cannot hope to have exact tracking. You will need to settle for some approximate computation. However, when the temporal variability is bounded, then some robustness results can be given. So the error, the asymptotic error on the gradient is bounded by some constants that depend on how well I know the internal model. So just to give you that, to give you the idea that it is possible to give some sensitivity results in this sense. We applied this to solve a control problem in transportation. So here to give an insight of the problem, we are looking at this transportation map on the left. So here on the left, we have Brussels over here. That's where we are now. And let's say transportation problem we're looking at is the following. So there is a town southeast of here called Wavre. And in the morning, many, let's say, many people working in Brussels, they commute from Wavre to Brussels each morning. So when they do that, we can model that, let's say, by using a graph where each highway is a link in this graph, and the traffic demand, so the number of vehicles per hour wanting to commute to Brussels in the morning, will be modeled by using an inflow lambda. So when we look at this problem, well, then it is easy to realize that travelers going from Wavre to Brussels have several possible choices to make to reach Brussels. So there are at least 3 paths in this graph to reach Brussels by using, let's say, different highways. So the question that we posed here is, well, how can the drivers choose the optimal path that minimizes their travel time to destination in every moment? We formulated it in this way, but if you want to solve a different economic problem, for instance, minimizing the total cost for the transportation, that can also be done with the same method. But here we focus on minimizing travel times. So this can be formulated by using the framework that I just discussed about. So the state of the network, I will call it X. X denotes the traffic flow on each highway of the transportation system. I will need to give some economic cost to the decision problem. I'm going to call Li the travel time of highway I. So this describes how long it takes to travel that highway. And then the problem of minimizing the travel time to destination can be written as an optimization problem. So at a high level, the cost that we want to minimize is this function. This has a particular structure. It is called a potential function. Then we have a certain constraint. This ensures that all the traffic that enters in Wavre needs to exit in Brussels. It is a conservation type of law. And then we have some feasibility constraints because we deal with traffic flows. Traffic flows must be non-negative. Okay, so that's how we can formulate that with the framework that I discussed. On the right-hand side, you see some synthetic simulation data. So at the top, you see an illustrative evolution of the traffic demand. So that is lambda. And you see here that this, let's say, model replicates 2 commutes. There is a morning commute between 8 and 10 a.m. And there is an evening commute happening between 4 p.m. and 6 p.m. So that's what this models. There is also, in addition, a high-frequency evolution in these signals, which describes, let's say, a smaller variation at the minute level. At the bottom here, you see the evolution of the state of the optimizer, as well as the evolution of the state of the optimization technique. So with the continuous line, you see here the evolution of the optimizers. Okay, so that shows that somewhat they reflect the high-level pattern that we observe in the traffic demand. And then what I would like to focus the attention on is on this part. So this is the transient part, where the optimization algorithm is trying to find an optimal splitting. So here what we can conclude is that after a transient of 1 hour and a half, roughly, the algorithm computes the optimal splitting, and then that splitting between the paths is, let's say, conserved over time. The algorithm is optimal throughout the day. Okay, so that's, let's say, an illustration of how these methods can be applied in transportation. I just want to give, let's say, two comments on strengths and limitations of these methods. So the first, let's say, strength of this technique is that the design of these methods strongly depends on how we design state observers for the temporal variability. And so here this figure is a little bit noisy, but what I want to focus the attention on are these three lines: dark blue, medium blue, and light blue. So what we can see here is that if we make the observer faster and faster, we can make the optimization method more aggressive and converge quicker. So that's one benefit of using observer as opposed to standard optimization methods where we are limited by the choice of the step size. And typically there is a fundamental bound on how those techniques can go. And then here in the other signals that you see in red, purple, and so on, is a comparison with the prediction error methods. So in reality, the parameters can be tuned so that one technique is better than the other in different scenarios. The other warning I would like to give is that all these analyses relies on local type of results. So what we say is that we can track the optimizers provided that we start close. If we start away from the optimizers, then we cannot give guarantees. But typically, this can be done by reinforcing the assumptions, by assuming that the equilibrium points of the temporal variability, the limit sets are unique or they are bounded and so on. Okay, so just a heads up on the limitations. So the next thing I would like to quickly talk about is on how to make decisions when transportation systems have non-trivial dynamics. Everything that I have done until now is under the assumption that the transportation system is evolving very quickly. The decisions we make now have an impact on the system immediately. This is not always the case. For instance, when we're trying to, let's say, to optimize a very large transportation system, for instance, here we have a study case in Los Angeles where we try to model the set of highways that loops around downtown in the city. Well, then, in this case, the dynamics are non-trivial because traffic entering in this moment will probably take about 1 hour to dissipate in this system. So that's what we observe in modern transportation systems. It takes some hours to, let's say, move vehicles from one part of the city to the other ones. So in this case, these type of systems have some non-trivial dynamics. Here I'm, for example, assuming that they can model by using linear dynamics. That is an approximation. Of course, they are non-linear in general. But what I am trying to stress is that there are some non-trivial dynamics that need to be taken into consideration. When this is the case, then let's say the decision-making problem I formulated earlier also needs to be modified. And one possible way to modify that problem is to look at optimal regulation problems for dynamical systems. So one formulation that I would like to illustrate is what I summarize here. So what we would like to do in this case is we want to choose an input state and output to this system. So the input is what I will call U, X is the state, and Y is the measurable output of this dynamical system. And what I want to do is to choose input, state, and output that minimize some loss function, okay, that measures the performance of that system. And I'm going to particularly focus on a cost function at the equilibrium. So here in the constraint, I am forcing the system to be at equilibrium. Okay, so this problem is what I will call an optimal regulation problem. I want to optimally regulate my system to an optimal equilibrium point. Very similar to what is done in extremum seeking, for example. So again, this problem on the left is parameterized by the disturbance W affecting the system. Okay, so this W enters the optimization and makes the optimization time varying. So similarly to what I had in the first part of the talk, this is also time varying optimization, okay, where I have one different problem, one different optimization problem to be solved at each time. Okay, and so here I can formalize the optimal regulation problem as follows. I want to design a feedback controller for you such that I regulate state, input, and output to the optimizer. Okay, there is just one more feature that I would like to give here. We can even allow the cost function to depend on time. So this is needed in transportation because, for example, the way people commute in the morning is different from the way they commute in the evening. In the morning, they travel from Wavre to Brussels. In the evening, they go the other way around, from Brussels to Wavre. And so we can allow for temporal variability in the cost. Okay, how am I doing with time? How much more do I have? 5 minutes, 10 minutes? Okay. So I just would like to give an insight of how these type of problems can be solved. So first of all, a few comments on let's say, the background on these optimal regulation problems. So these optimal regulation problems are very much related to what has been done in control in the context of output regulation. It is also very much related to extremum seeking. We have done an interesting talk on this last week. So these problems are related to extremum seeking. And of course, they are related to model predictive control, optimal control. They are related to many problems in control systems. But what I would like to emphasize is that these problems that I'm talking to you about is a relatively emerging area of research that now goes under the name of feedback optimization. And here I have a non-exhaustive list of researchers that contributed to this field. It is non-exhaustive by many means, but I just want to give an idea of where I see this going. Okay, so just to give an insight of how this can be solved. So the problem, the optimal regulation problem I described, in reality is, I formulated as a constrained optimization problem. But these are the quality constraints, and therefore I can eliminate the dependent variables. And so in reality, I can rewrite it as an unconstrained problem. And so these functions G and H are functions that depend on these 5 matrices that can be computed by them. So in reality, while it is written as a constrained problem, in reality it is an unconstrained one. Again, here we can apply methods connected to what I talked about in the first part. We can apply, for instance, the basic gradient flow method that I described earlier. But maybe since I believe I am running out of time, I would like to get to talking about how this can be used to solve transportation problems. So this is, let's say, a set of results that we applied to the ramp metering problem in transportation that I would like to talk to you about. So the ramp metering problem is the following problem. So we look at a stretch of highways, at a set of highways, and a set of highways we can again model it by using a graph. So it is each highway is modeled by an edge in the graph, and points where highways merge or diverge, they are nodes in the graph. And the ramp metering problems have one particular feature. So if we take one of the nodes of this graph, each node of this graph is a point where vehicles can enter a new highway or can exit the highway. So ramp metering consists in placing a traffic light at the entrance of that highway, and by regulating the green time, so how long we give the green to vehicles, we can regulate the traffic flow that is entering the traffic system. Okay, and so the objective of ramp metering is that of controlling these traffic signals, controlling how much green time we give, in order to maximize the throughput of vehicles through the entire network. So just a few words on how this is done until now. This is typically solved through very simple control methods. There is a PI or PID type controllers that are applied only locally, or transportation engineers run a simulation-based approach. What that means is that they do Monte Carlo simulations based on different scenarios and so on, and they optimize their choice of lights. It is worthless saying that both these two methods have limitations. First of all, local controllers are suboptimal because they don't look at the entire network, they only look at what is happening locally. And if you do a lot of simulations, it's also suboptimal because in that case, if traffic conditions change, then the controller implemented will still be suboptimal. Okay, so what we want to do is instead do something, let's say, more advanced and apply the optimization method techniques that I talked to you about. So here you have an illustration of what can be done. It is a little bit of a busy slide, but on the left, this is a way we can model the transportation system. There are models, macroscopic models of how this can be described. The most popular one is what is called the cell transmission model. It is a model that describes how traffic densities evolve with time. So this is a dynamic model of transportation. And then we can formulate the ramp metering problem as an optimization problem. So what we want to do is we want to maximize the throughput through the network. We want to try to meet the demand, so let everybody that wants to go to Brussels go as much as possible. And then we want to ensure that let's say all the highways remain in free flow. We do not want to accumulate congestion. And that can be done by formulating constraints on the optimization. So here I have, let's say, some comparison between different techniques. I mainly would like to focus on this figure. So what this figure shows is, as an evolution of time, it shows the throughput through the network. So if we do no control, then I obtain that, let's say, that doesn't perform very well because when the traffic demand is very high, the whole network becomes congested. On the other hand, if I use a PI or PAD type control, then I already obtain some sort of improvement. But the techniques that work the best is when we do network-wide optimization. So when we apply either MPC or the techniques that I talked to you about, which are these two plots over here. What I would like to stress is that MPC struggles when there are unmodeled changes in traffic congestion. Well, on the other hand, the dynamic methods that I have been presenting today work much better, even if they use a simplified model, work much better when there are unplanned changes in congestion. Okay, so there were other transportation problems I was excited to talk to you about, but I think I am running out of time. So I just would like to come to my conclusions. So transportation systems are becoming increasingly fast. And this poses the need to develop methods that can adapt quickly in response to these fast dynamics. What I try to emphasize is that optimization methods, how they have been developed by the optimization community, are not suitable to make decisions in time-varying environments. The basic gradient flow fails or is inapplicable in many cases. I give you a fundamental limitation, which is that we can guarantee optimality and tracking of the optimizers only when we have an internal model of the temporal variability. If we don't have an internal model, we will have to settle for approximate optimality. I also discussed a little bit the problem of dynamical systems. So when we are trying to optimize transportation systems at a network-wide level, then their dynamics are non-negligible. They are fast, but they are not infinitely fast. And accounting for those dynamics mandates the use of the techniques I hinted at in the second part. And the main finding that we have there is that what can be done when the transportation system has non-trivial dynamics is to use optimization methods that are slower than the transportation system. I haven't touched much upon this, but I'm happy to discuss it offline. With this, I would like, of course, to thank the funding agencies that supported this research and the many collaborators and students involved. And thank you very much for the attention.
So, are there questions? time for questions.
Thank you for the presentation. Could you go back to the last thing you said, that the optimizer needs to be slower than the system? Which, whenever I work on MPC and do similar things, I say the exact opposite. So I just wanted to ask if you could go deeper into that detail.
Yes, so that is an excellent question. So I admit I have not covered this topic in the interest of time. But the main result that we have in that case is something like this. So in this case, what we are trying to do is we have some plant with non-trivial dynamics, the transportation system, and we are controlling this transportation system by using an optimization algorithm, such as a modified version of the gradient flow. So the analysis of, and let me stress maybe one more thing, the control problem we are solving here is an optimal steady state regulation. It is different from MPC.
Okay, yeah, that makes.
In that case, what we can do is borrow some analysis from optimization. And the general message in optimization is that if you use a gradient descent iteration with a sufficiently small step size, everything will work. And here the message is the same. I need to use a gradient flow type of iteration with a step size sufficiently small. But yes, this is, let's say, a main gap between steady state regulation and MPC. While MPC focuses on transients, this steady state regulations is more concerned about the steady state.
So since you're interested in the steady state, the plant needs to be fast enough that it goes to steady
Exactly.
state before
Faster
optimize.
than the controller,
Okay.
yes.
Okay, makes sense. Thank you.
Other questions? Well, if not, I would thank again Gianluca